Hey, this is Horner. We're going to look at the pretest questions number 1 through 10 for the AP Physics C rotational motion pretest. In this first question, you have two wheels. So here's one wheel. You've got another wheel on the outside. They are connected to each other. And then there are four forces pulling on the two wheels. There are three forces actually pulling on the outside wheel, and you only have one force pulling on the other wheel. They want to know what is the magnitude of the net torque on the axis. Do notice first, what we're going to do is just kind of draw some lines of action. So for this first force over here, this is at 90 degrees. We notice that this line is at 90 degrees. From the center to here is 90 degrees, and from the center to this force is also 90 degrees. So at this point, we know that any torque we have is really just RF times the sine of 90 degrees, and that sine of 90 is 1. So when we look at this, we're just going to go ahead and get rid of the sine of 90, knowing that we have just radius times force. So let's number each one of these forces. This is going to be force number 1. Let's do this one as force number 2. It really doesn't matter how you do these. You just want to make sure you label them all at some point. Number 3, and then this will be force number 4. Remember, any force that is going in this direction, which is counterclockwise, is going to be a positive, and any force going in this direction, creating a torque that will be clockwise, and that would be negative. So for number 1 itself, we'll see that this one is going counterclockwise, so it's positive. For number 2, it is going clockwise, and so we know that one's negative. And 3 and 4 are both also going positive because they are going clockwise. So at this point, we know the sum of the torques should be equal to, and we've got torque number 1, which is positive, minus torque number 2, plus torque 3, plus torque number 4. We said that for each one of these it's RF, so this first one will be equal to R1F1 minus R2F2 plus R3F3 plus R4F4. Now at this point, we're going to plug in the values that they've given us for each one of these. So for number 1, we'll notice that it's all the way out on the outside, so that is a value of 3R. And then our force for this one is just F. We're going to subtract from that the another 3R, because this distance here is 3R, 3 times the radius, and this one is 2F. Then we're going to add to that number 3. Notice number 3 is only at 2R, but it only has a force of F. And then finally, the last one is a radius of 3R with a force of F. Now what we can do throughout this is go ahead and factor out an R and an F. So we have RF, and then we have 3 minus 3 times 2 is 6, and then we have plus 2, and then the last one is just plus 3. So 6 minus 3 would be negative 3. Plus 3 would be 0, so we see that we have 2 standing out, and so our final answer for number 1 is 2 times R times F, or they have it as 2FR. So this answer is letter C. For number 2, we have a problem that doesn't have any picture to it, which is usually a good thing. And it says you have a wheel of mass M and radius R rolls without slipping, so there's no slipping here. If the angular velocity of the wheel is omega, what is its linear momentum? So the first thing we need to do here is go ahead and think about the velocity of the center of mass. For this, if it's a wheel and it's rolling and not slipping, we know that this point is going to just move to the right. So that's a very linear motion as we go. So now we've got this is equal to the radius times omega. Remember, our linear thing is always equal to our angular thing times the radius itself. Now that we know that, we're going to use the linear momentum equation, which is just mv. And at this point, we can go ahead and give it some angular motion here. So m stays m, and then our velocity, remember we said, is r times omega. The only one that is m omega r or m r omega is letter A. For number 3, this is the next problem. For number 3, it says we've got these two wheels that are connected to each other. They rotate about a central point. The inside one has a radius of A, the outside one has a radius of B, and we have two masses, M1 and we have M2. So what we'll do for this one is we know that if they're going to be in static equilibrium, if they're not moving, we need to make sure that the two torques are going to be equal but opposite. So we know that the sum of the torque about the center of this object should be equal to 0. And so we know that that is torque of the first object. So that's torque of wheel 1. And we're going to subtract then torque of wheel number 2. So wheel 1 and then we've got wheel 2. The reason that we're doing, well, let's just go on here. Those should be equal to 0. And so we can now put them on either side. So torque of wheel 1 should be equal to torque of wheel 2. One of them needs to be positive and one needs to be negative because they are being torqued in opposite directions. This one is torquing in this way, and so we say that that one's positive, so that could be our W1, and then wheel 2 is torqued in the opposite direction, and we know that that's clockwise, so that's got to be negative itself. At this point, we need to go ahead and put in our equation. So torque for the first wheel is going to be equal to the radius times the force. And our force for these is going to be the mass times gravity. So we're just going to call this one weight 1. And that should be equal to the radius of number 2 times the weight of the second object. The radius for the first one is actually A, so we're going to call it A, and then weight would be M times G, and this one would be M1 times G. And for the second one, this is B, and this one's going to be M2 times G. At this point, we can go ahead and cross off our G's, and we're left with AM1 is equal to BM2, so AM1 is equal to BM2, and that is our correct answer. Notice that they have one without any letters, which wouldn't make any sense. This one does have the letters, but you'll notice that the subscripts for the M's are backwards. You wouldn't square it, so we're not going to worry about those at all. So 3 of the answers really don't make sense. 2 of them are very similar, and you need to pick the correct one. For number 4, this one says I have a wheel with a rotational inertia I mounted on a fixed, frictionless, so let's move this back up, mounted on a fixed frictionless axle. The angular speed omega of the wheel is increased from 0 to omega f in a time interval t. So this has got to be some sort of kinematics equation problem. For this one, we're going to start off by thinking about what we know. We know I, so we know moment of inertia is I. We know that the initial velocity here is 0. We know that the final velocity is something that we're looking for. And then our delta t is really equal to t. And so we're trying to figure out also what's the sum of the torques going to be equal to. So it says, what is the average net torque on the wheel during this time interval? So that's why we're looking for this net torque. For this one, we just know that torque is equal to I times alpha, where alpha is our angular acceleration. For this one, then we could say I times, and remember alpha is angular acceleration, so that's just change in angular velocity divided by the change in time, which then would be equal to the final angular velocity minus the original angular velocity, all divided by capital T. And at this point, we can go ahead and think about the fact that our final angular velocity is going to be a value, but we don't have any value for the original, and we divide that by time. And so our final equation is just I times omega final all over t, and that one would have to be letter E. So that one's got to be letter E. So another problem that's pretty simple to do. You just have to work through the algebra and make sure that you have it correct. For the next problem, this is going to be number 5. It says, what is the average power input to the wheel during this time? So for number 5, we've got to think about what power is. We know power is work over time. We also know that power is equal to force times velocity, where the force we're not worried about because it's rotational form. We can go ahead and put vectors over the power and over the velocity. Um, Remember, for angular motion, this one's going to become power is going to be equal to the torque times the speed. And if that's true, then let's go ahead and plug everything in. Torque here is going to be equal to what we had before, which is I omega final all over time. And then we're going to have the average angular speed. So that's the omega final plus omega original or initial, and that's divided by 2. So this is average power, and then this is average speed. That's what the lines above are. Notice they're not vector signs. Vector signs are like this. So this indicates that it has a magnitude and a direction, and if it's just this, then this is going to be an average. That's the difference between the two. We know that this value is actually 0, so when we're done, we're going to have I omega final squared, because we multiply the 2, and that's all over 2t. And if you look, that would be letter B for our answer. And we're going to stop here, and we'll do the next video for number 6 through number 10.